Welcome back. The next task we are going to perform is the regression task. This is a new task we have in this. This is the first time we run a regression task in this hands-on workshop. And for this task, I'm going to use the generalized linear model, the machine learning algorithm, which can be used for binary classification and regression purposes. So in this case, we have a regression. I'm going to refresh the data again from my customer insurance table in my database to be used for training and testing. So I'm going to recreate the data frame and synchronize it again with the data I have in my database table. And as usual, as always, I return the first 5 records in my data frame just to make sure what kind of data I have. I'm dropping the LTV bin column because as this is not a classification task, I don't need this column with those classes of customers, low, medium, high, and very high. And in this case, we keep the LTV column, which is the numerical column with the actual value a customer has for our business. You can see it here in the last, at the end of the output. And I'm going to use this column for the regression task. I'm going to perform a split now. This is going to be using the the default ratio 70-30, I think it is, between the training and the testing data that's going to be used from our data frame. And then again, this model, also the generalized linear model, also requires the training data to be specified in 2 objects, attributes and labels. So the train X is going to be with the attributes, train Y with the labels as before. And the second part of the split is going to be used for testing purposes. And then I'm going to return the shape of this matrices of the objects I'm going to use for training and for testing. So let's run the block. We have here 10,000 rows used for training with just the labels, 29 columns. 10,000 rows again for training, but with only the label, the result, the LTV value, numerical value. It has 1 single column. And 4,600 rows we're going to use for testing our machine learning model. And then we're going to specify some settings. In this case, I'm going to use just one setting of this machine learning model, the solver. I'm going to specify the solver to be a stochastic gradient descent. So this is the single setting I'm going to provide for this model, and the rest I'm going to leave the default values just to show you how it works. If you want to see all the settings you can use for a specific algorithm and a model, you can click here on the link, and it will take you to the full list of settings you have for this machine learning model in particular. And then I'm going to create the generalized linear model with the settings I just created in the previous block. And then I'm going to fit the training data into the model I created. So I'm going to use the train X and train Y for the training as the training data for my model. And then I also specify the column I'm going to use to identify each particular record, each customer case. In this case, the case ID, which is the cust ID column in my data frame. So this is used to identify the unique records in my data frame. And then I'm going to output. I'm going to print the details of the model I just created, of the machine learning model. It's a generalized linear model for regression, and I can see here the solver is the stochastic gradient descent, and then I can go and look at the all other settings, global statistics of the model. But maybe one of the important attributes of this model I just created is the convergence. And if the model has reached convergence where I can use it to retrieve predictions for my data, and I'm going to return only this attribute of the model. So it is false. In this case, it means that my machine learning model has not converged, and I cannot use it to reach a prediction for some records I have without a label in my data. This is why I need to change my model. I need to specify different attributes, different settings when I create it, and I can try different options. The only option that comes into my mind is to change the solver here, and maybe there are other options, but in this case, in this particular example, I'm going to change the solver just to show you how a model can be recreated and improved in case you don't reach the convergence you need. So now I'm going to use the Koletsky solver for this generalized linear model, and I'm going to recreate the model again for regression task using the new settings. And I'm going to retrain the model with the trained data, and I'm going to use the same column for identifying individual customers in my data to be used in the regression task. So now it is using the new solver, and the model is training. It takes maybe a little bit longer than the previous one to get trained. And voila, my model has been trained, and now I can check again the converged attribute. And now the converge is true. So it means that I can use this model to return regression predictions for new records, for records without a label. So in this case, I'm going to use the model to make some predictions, and then I'm going to drop the LTV value from the testing data, just not to provide the actual answer to the model when I'm requesting the model to give me the answer for this value. But then when I output when I return the results, I'm going to include this value again, just to compare it with the predicted value. So I'm going to use 3 columns to identify my customers, plus the pre-label I already have to compare it with the predicted value. And here it is. I have the 3 columns to identify my customer in my data set, in my test split of the data set. And then I have the actual value, which has been provided in my data set for training purposes, and the predicted value, which has been returned by the system. We can see here there is a difference between the actual value and the prediction, but the difference is not very high. So we don't have a big difference between the the actual values and the predicted values. As this is a regression, here we can have any numbers, because the regression, we don't have fixed values as for the classification tasks. The model can return any number based on the attributes we have in the data and based on the data we use to train the model. The more data we have, the better the model it is, and the best results we will receive from a regression task. Now we can also return the probability for the predictions, so you can we can understand how convinced is the machine learning model that the predictions are accurate. So in this case, I don't have the probability column here in this output. I don't see it, but it means that the probability is not returned basically for this particular model. I'm going to investigate why, but I'm going to make just an adjustment to the output to return the difference between the actual value and the predicted value. So I'm going to run this just to keep these two columns. I'm going to filter my data just to keep these two columns, and this way I'm going to analyze the difference between the actual value and the predicted value. So I can make calculate the difference in this next code in the new column. Let's say I'm going to have this column with just the difference between the actual value and the predicted value, and then I can concatenate the difference with the results I have in my filtering here with the other with the rest of the output. So this is the actual value, the predicted value for my customers, and this is the difference here. So these are just the errors from the execution of the model. Let's say the difference between the actual value and the predicted value I have in my machine learning model execution. And in order to understand it, to see if this value is high or low, and what kind of differences I have for my entire data set, I can run a plot here with just the differences on the vertical axis and the customer value on the horizontal axis, on the x-axis. So here, for example, you can see that for the customers in the middle, for which I have more data, actually, I may have bigger differences. I don't know if I can increase the size of this. Let me see if I open image in a new tab here. So in the middle, I have more data, I have more customers, but also I may have more higher errors between the actual value and the predicted value for the regression task. And you can see the errors are evenly split between negative errors and positive errors. This means that the model returns both undervalued customer and overvalued customers from the test data I have used to run the model and to verify the model on. You can check here, you can see that for the very high customers and for the low customers, the error is smaller, but in some cases I have more under evaluated or negative errors in my outcome. So it's a subject of interpretation here. So it is the more data we have, maybe we will be able to improve this model and make it more accurate. But the data we have used and the settings we have used now, it gives us this kind of let's say error, and the error is not so big. For example, for some of the customers, the error is just in a couple of a few hundreds points for a single customer. For most of them, it's very small. But also we have customers with huge errors. For example, here we have an example, and in this case, the error is 10,000 points. So the actual value of the customers is 28,000, and the predicted value based on the customer attributes is 18,000. So we can see here between the actual value and the real value of the customer, which has been calculated by the machine learning model, we have a difference of about 30% of the actual value of the customer. So you have to use your interpretation and understand why this customer has been predicted with such a value. And this is it. Thank you very much.